Introductions to Calculus. First you learned algebra, then they tried to teach you geometry. Then they tried to explain trigonometry to you. But now, calculus students, you finally accomplished becoming strong calculus students. Calculus had many controversial inventors. Sir Isaac Newton, the first one, was born January 4th, 1643, and he died March 31st, 1727. He was an English physicist, mathematician, astronomer, natural philosopher, alchemist, and theologian, who has been considered by many to be the greatest and most influential scientist who ever lived. His monogram was Philosophus Naturalis Principia Mathematica, published in 1867, lays the foundations for most of classical mechanics. In this work, Newton described universal gravitation and the three laws of motion, which dominate the scientific view of the physical universe. For the next 3 centuries, Newton showed the motions of the objects on Earth and the celestial bodies are governed by the same set of natural laws by demonstrating consistency between Kepler's law of planetary motion. The second inventor of calculus is Gottfried Wilhelm Leibniz. Leibniz occupies a prominent place in the history of mathematics and the history of philosophy. He developed the infinitesimal calculus independently of Isaac Newton, and Leibniz's mathematical notation has widely been used ever since it was published. His visionary law of continuity and transcendental law of homogeneity. Leibniz made major contributions to physics and technology, anticipated notions that surfaced much later in philosophy, probability theory, biology, medicine, geology, psychology, linguistics, and informational science. He wrote books on philosophy, politics, laws, ethics, theology, history, and philosophy. Leibniz's contributions to the vast array of subjects were scattered in various learned journals, in tens of thousands of letters, and in unpublished. Now, Leibniz and the Newton controversy. Basically, Leibniz published his full work on calculus in 1684. That was 9 years before Sir Isaac Newton published anything on calculus. Newton didn't do a full publication on calculus until around 1704, but he claims to have started calculus in 1666, but did not make a very broadcast about it because of controversial and criticism. Leibniz notations are far more used notation in calculus. Newton claimed he started working on calculus because of controversy and criticism. It's hard to believe that Newton, a very well-respected man in the scientific community at the time, would fear controversy and criticism when developing a new branch of math that could only further his cemented legacy. The story doesn't end there, though. Guillaume de la Hopda later created a publication on Leibniz's calculus, pointing out that Newton's principle, published in 1687, publication was also about calculus. Plus, Leibniz studied Newton's work in 1776 before his publication of calculus, so it is very likely that his calculus could have been based on previous works by Newton. Also, when you look at all of Newton's contributions to science and mathematics, it's very unlikely he would copy someone else's work and claim it was his. In conclusion, though, I think Leibniz did invent calculus, but based on previous works by Newton.
Hi, my name is Kane Jacob, Ajani Benitez's partner, and today we will be teaching you about how calculus is used in the world and the different examples of calculus in the world.
Calculus can be applied in many real-world experiences. In this video, we will be showing you several of them. Okay, what we're going to be doing right now is finding out the rate at which the volume increases in this cylindrical cup. Now, from our research, we found out the water is coming in this cup at about 1 inch every 10 seconds. So from that, we're going to be able to find out the rate at which the volume increases from various things, from like we're going to use the radius of this cup, we're going to find the overall height, and then we're going to be able to get a good estimate. What we're going to do now is find the rate at which the volume is changing in the cylindrical cup that we were just filling with water. So now what we're going to do is start using what we already know. We know the equation for the volume of a cylinder is pi r squared times height. So to find the rate at which volume is changing, dV dt will be equal to, since r remains constant So this pi, because r does not change in the cylinder. So it's going to be pi r squared dh dt. Now we established that dh dt is equal to 1 inch every 10 seconds. So, or better yet, 0.1 inches every second. So what we're going to do now is plug in the values. So we have, and r is also established at 2.5 inches. So dv dt is going to be equal to pi 2.5 squared times 1. And then simplify that, you're going to have 6.2 pi times 1, so we just leave it as that. So the answer is dv dt is 6.25 pi feet cubed. Okay, what we're going to be doing right now is reorganizing the room. So to reorganize the room, we're going to use integration to find out the area of these various objects. For instance, we have this rectangular keyboard. And what we're going to do is show it on a simple equation to find out how much space this is actually taking up. So from our measurements, it's about 5 feet by 1.5. Now what we're going to do is use integration, and we're going to actually show you on paper what it looks like when we solve how big of a space this is taking up.
We're going to find out the area of the keyboard. We're finding the area of the keyboard through integrals. So b, upper limit, lower limit of f of x dx. The upper limit of the keyboard is 1.5. The lower limit of the keyboard is 0. F of x would equal 5, and of d of x. So now we have 5x to the 1.5 after integrated, and this would equal 7.5 minus 0, which would end in 7.5 feet. Swag.
Today what we're going to be doing is finding the average rate of change for the time it takes for this 1 cup of water in this teapot to boil. So we're going to start the fire and then come back once it begins to boil. We're going to turn off the fire now, but the water just began boiling.
The 1 cup of water just reached its boiling point at 212 degrees Fahrenheit, which is also 100 degrees Celsius. So now we have to figure out the average rate of change that it took from the room temperature amount of water and the boiling point that is 212. Today we'll be doing our third and final example, instantaneous rate of change of the change in temperature of the water boiling. So we have T prime x equals T b minus T of A over B minus A. So T prime of x, and when you plug in the actual values, is T.24 minus T of 0 divided by 2.48 minus 0. So now the actual values are 212, which is the temperature of the water boiling, of the boiled water, minus 72 degrees, which is the room temperature, divided by 2.48 minus 0. So that would equal 140 divided by 2.48 when you subtract, and this equals 56.5. 56.5 equals the degrees per minute. Slide.
I'm Mr. Aristotle. Yes, I'm friends with Ajani and Kane, and I think they deserve probably 95 in your class. Ajani et Kane, yo mérité un 95 sur le podcast yo.
Aisha got a 3 on this test. That is 3 reasons why we should get a 95 or 100 on this project. And since you're such a good teacher, Mr. Aristotle, you got Aisha. No, I messed up.
In the real world, and Yeah, I've done it mad times.
Johnny, you never did it before. Yo, Johnny, is this gonna be in our video?
Yeah, it'll be mad.
Talk about the velocity of nothing.
So I'm climbing up this tree right now at a steady velocity, Mr. Aristotle.
John, why are you calling me down?
No, I'm hit. Boy, you okay? Kane, I've never been to the top, bro. I've never ever went to the top. No!
Nobody ever went to the top.
Nah, but you almost did it. You might as well. Just check. Ah! Nah, if you die, Kane, if you die, this would not be funny. I'm gonna have to delete the video. I'm gonna have to delete the